So we thought that a specific code for the worker interface will reduce the error probability. And this is why we chose not to go with RTFlow API, but we chose to use the control as the RTFlow template API, because RTFlow template API, we had a presentation yesterday about it. I really like it. And it gives a good separation between control and data path. This good separation means that the pipe that I showed you here, I can build it very easily using RTFlow template API. Just allocate the structures. I know the sizes. I know how many connections I'm going to support. I know how many D caps and N caps I'm going to need. And I know how many queues I'm going to need. So all of this I can already pre-allocate. So RTFlow template API is just great for giving us this already implemented control. We didn't want to re-implement everything. It's just incorrect. But we did choose to go with a device-specific interface. This device-specific interface is what runs on the worker, and it allows us to do all of those configurations really, really fast without RTFlow. Another challenge that we had with our interface is how to expose it. We have different instruction set architectures, and all of them are running the same application. Current DPDK has a single toolchain. You can compile it to ARM. You can compile it to x86. You cannot compile it to 3 different devices and have the same application. Another fact is that the device workers that are implemented, they need some H file, right? They need to run our interface. And another need was the source. We don't want to provide the sources. We want to provide an already compiled library for them to link to. And as I said, we need to support in the same project multiple architectures on the same build. The solution we came up with is we didn't want to diverge from DPDK, so we wanted to provide DPDK with multiple cross-compiled device library, and we integrated this to DPDK using a custom target. A custom target is a Mason option, so this means we can compile DPDK, get the libraries that we need, and those libraries and H file are used by the developers who want to run their code on those different devices. I'm switching to device challenges. Until now, we talked about interface challenges. Let's talk about the device challenges. So the problem is we have multiple worker devices. All of them are running in parallel. We need to synchronize all of those together. Packets are processed in parallel over those devices. RSS splits the different packets to different workers. They're running in parallel. They configure the same object in parallel. The city table is shared between all of those devices, and all of those devices want to configure this city table. Each one has its own 5 tuple that it wants to configure, and everything is happening in parallel. There is no memory access from those devices. As I said, the address memory space. So we cannot have some lock, and we also don't want to have a lock because it will slow us down. So the solution we came up with is it consists of 2 parts, the solution to synchronize everything. The first part is RSS. RSS ensures a fixed distribution for the incoming connection between the workers. The second one is hardware synchronization. Our hardware supports everything below is implemented in some sort of data structure, and our hardware below know how to lock it, how to lock certain things in it, and add the configuration, and synchronize all of those configurations coming from different devices and set them correctly on the same hardware object. So with those 2 means of synchronization, we're able to run the code in parallel on 2 devices, no locks, and in high speed. Another problem that we had is the limited memory system. What is the problem with the limited memory system? It's not limited only in the amount of memory. It is also almost impossible to allocate memory in runtime. I guess it's possible, but it is something which is very expensive to do. You need to go to the host, ask for the memory, get it back. We understand that it's not a runtime solution to allocate memory, not a data path solution. And we don't have an efficient runtime memory allocation, as I said. And as I said it a couple of times, separate memory address space, which is another challenge. The solution we came up with is pre-allocating the memory. based on the template API. Template API does it very well. We know how many structs we'll need, what are the sizes of those arrays that containing those configuration. And another method we used is batching. Whenever we need to synchronize something to the host, we would not just access the host. We would gather a couple of configurations and then move it to the host. So batching also helped us a lot to get good performance. So I talked about the challenges. Let's talk about the interface we used for those workers. We see here that our interface consists of two parts. We have the device and we have the host. The host API is used for control. It is called from the host running the DPDK application. This host has access to the operating system. It does the port initialization. It does the capability checks. It does all of the things that are needed to be done in the control phase. It also prepares and allocates the device memory. So this host is able to allocate resources on device A, and he is also able to allocate resources for device B. With the regular RT template API, we can create an RT flow template table. And now we're left with the other side of the device interface, which is the device interface. The device interface is used on the device worker. This is what was being run in the orange and green boxes that I previously presented. It is used to insert and delete the flows, to insert and delete those configurations to the city table. And because the RT template API is asynchronous, so we also need to poll for the completion and see that, that our configuration was successful. Another key thing that we had with allowing two devices to work in parallel is the bind and unbind logic. So what is bind and unbind? You create a device object, a native device object on your application, an RT flow template table. Now you want to access this table from two different devices. So what you can do is you can bind your table to a non-native, to a cross-compiled device table. This device table, it resides on the device itself. And you can also take the same RT flow table and take it to another device. So the device object is different between devices. Internally, it is the same, but it is allocated on different memory address space. And it allows us to run multiple devices in parallel over the same RT flow, a heterogeneous system running on multiple devices. The device object is minimal, of course, because RT flow is very generic. We want something minimum. We want something to run as fast as it can. So this is a key thing here, which is part of the host API, the bind and unbind function. Here is some pseudocode of an example of what developers need to do if they want to run on those devices. What we do is we have the host process. We open the process. We provide the port ID and the device info, ARM, DPA, whatever device you want to support, and you get back a device process. Then you need to create your RTE template table. After you have your RTE template table, you need to bind it. You need to bind it, and you get a device table. This device table is not accessed by the host. It has some memory address which is not accessible by the host, but it is accessible on the device. And if we're able to pass this device table to the device interface, the device can add configuration. So now we have the device table, and here is the device. The device calls the specific configuration function called device CTV4, create the flow. It specifies the queue that it wants to run on because everything is running in parallel on different queues. It specifies the device table that it got, the specific 5-tuple that he wants to offload to the hardware, the actions that the device wants to execute, and he gets back a connection. By the way, this connection is pre-allocated, meaning the device has to have a big array, a big pre-allocated array. He needs to manage it, and he gives the memory for us to initialize it because we don't do any memory allocation, as I said. Then we need to do active polling to get a completion, to see that this configuration was successful. It also helps us with synchronization to know when something was done, because configured, saying I started the configuration does not mean that the hardware applied this configuration, and this allows us for a method to know that something was done. And lastly, if the device wants to destroy connection, we have the destroy function. Again, it gets the queue, you pass the connection that you want. This connection is exposed to the device, so the device can even utilize things by keeping his 5 tuple on the connection and say connection pointer to source IP, and then it can save even more memory. So as I said, this is not a comparison between software and hardware city. This is not what we were aiming for. Hardware city is much, much faster. This is an attempt to run a heterogeneous system application on the DPDK. So with our RT flow template API, we were able to increase the connection update rate in 20%. So on the same ARM core that was running RT flow API, using our specific interface, we're able to speed things up in 20% by reducing checks, by doing specific work compared to the generic work. We're able to double the connection update rate by utilizing all of the DPU capabilities. So once we decided to run on all of the processing power that we have, we're able to double the performance, double the amount of connections we can offload to the hardware. And we're talking about, it's more or less 8 million connection updates per second. And again, updates, not configuration, it's configure and delete. And all of this is done with 0 effort from the main CPU. The application is running on the DPU, the hardware executes those offloads that are being done. Any questions?
Do we have any questions from the in-house?
Yeah, one thing that if you could go back to this one of this architecture slide where you had a host and a DPU core and yeah, it could be that. So you told that you compiled the DPDK on the worker as well, right? But that was some kind of embedded processor, perhaps no virtual memory or whatnot. That's why it couldn't compile like the whole DPDK because it didn't have huge pages, memory allocators, what's not, right?
Right.
But internally, it still used DPDK API to connect to the hardware CT.
Yeah.
Is that correct?
Yes.
Okay, so it would basically, it had some kind of a PAB driver to implement this specific stuff.
Yes, yes. We have some specific part and we have some general stuff. The general is the host.
So how complex was it to separate all the DPDK code base into this embedded friendly stuff and application CPU stuff?
Okay, so I don't want to brag too much, but it wasn't very complex. We're able to do it, I think, in 1 month. The main reason for that is the template API. The template API, it has a very strict split between control and data path. So the control path, we didn't need to implement anything for the control path. We had everything already implemented. Once we were able to do all of this, then we were just left accessing the city table. And accessing the city tables means we need to expose some bind functionality. And of course, we know how to access our own hardware. So on the device worker, we were left for just configuring this table. So it wasn't too complex to do with the new API. And we also had here a specific use case. We did not plan to support everything. We added the support for the things that we need for this use case. We chose it, I also presented it, because it was it was challenging. We thought maybe let's have everything, and then we understood that if we'll have everything and we'll have something which is generic, it will just not run fast on those slow processors.
Yeah, so my next question would be, would it make sense to actually make it more easier for others, or make it, reusable in the future, like carve out a subset of DPDK that could be run on the embedded devices that don't allocate memory, because I guess it's not, that use case would be, we will be going to see this in the future more than once.
So I totally agree with you, and as I said, this is the way current SmartNICs are going for. From generation to generation, we just get the next generation, and it has more capabilities, it has more processing power, and we need this processing power. It can really help us with our offloads, with our configuration, with packet processing, and I want to believe that the DPU will be the next GPU. When someone will buy a DPU, it will do all of its network processing.
Thanks. Thank you.
There's another one from me. How do you split up the traffic in this RSS element? Because I envision if very similar 5 tuples come in your 8 million create, read, update, and you end up steering them all to the same worker, maybe to the low performant one, you would see a performance degradation.
What do you mean by same ones? You mean the same 5 tuple, the same connection, or you mean 2 different connections?
Multiple different connections that for some reason the RSS element decides to send to the same guy.
Yeah, so of course this can happen, right? We can have a device that gets 2 connections at once, but RSS, it calculates a hash, and we can even control the hash we want to calculate, meaning on which fields we want to do RSS. And usually when we're talking about different connection at a real system, it is spread quite evenly over the devices. This is what RSS does best. RSS, of course, is implemented also in on the kernel, hardware RSS, on our network device, and it works well.
Yeah, thanks for the talk. If I got it right, then actually you have to write 2 programs, like one for the host, and then you have to write another one for the NIC. Is that true?
Yes. You need to have your main DPDK application doing the host stuff. It does the initialization, it does the allocation of this whole pipe, it does the binding, and the DPDK application, its goal is to have those device tables. Those device tables, we need to pass them to the device, and those are 2 different devices. So our developer said, wait, so now we need to develop 2 different workers. One is ARM, one is the DPA. And we said, no, why do you need to do both? If we provide the same interface for those 2 devices, you can basically have a single worker, worker.c, and both workers are doing the same. There's no difference between them. Yes, they're compiled differently, but they're running over the same interface.
But I mean, still I have to write somehow 2 programs. So this is no longer portable across NICs, because this is just a solution that works for this particular NIC.
Again, we provide the interface. The interface is offloading. The interface, what it does is offloading. As someone who develops a DPDK application, you use the interface for your worker. So you write your worker with your logic. We didn't expose the logic of the application. We didn't say, get the first packet, see if it is valid. No. We just exposed a way for the worker to access the RT table. So it's something which is, it still stays generic. Yes, it is specific for CTV4 because of the performance, but it is generic in terms that you can develop other use cases on top of it, and it is just the interface.
Okay, thanks.
So with the device A and device B workers, they're differing architectures. Do you foresee an opportunity where their capability set might be such that one is more proficient in handling connection type A and one is better at connection type B, and then the RSS has to kind of steer A and B to the right worker to increase performance?
Yeah, it's a good question because if we're talking about CPU and GPU, of course you want some things to be done on a GPU and other things to be done on the CPU. Luckily for us, those processors, both of them were, both devices, they were quite similar and quite slow, and the implementation was really very, very minimal. And we wanted to use everything that we have, like all of the processors that we have. But I think that you can, of course, write your application, and we provide the tools. What do I mean by tools? You can open an RSS. You can decide to how many different workers you're going to run, how many different threads are you going to run, how many different receive queues are you going to have. So you can tune it. Let's say you want 2 workers per core. It is also possible to run 2 hardware threads that are running on the same core. So you can balance it. It's not a fixed solution that says 3 here and 3 here. This is only a picture. But I think it's a good question on how to expose the different capabilities. I think that the user, if we in the future will have really different devices, then somehow the user needs to understand this and decide what he wants to run where. But the idea here is how to expose this interface to the user and keeping it still generic, not too specific, to run other use cases as well. But it's a very good question. I'm happy to see there are a lot of questions.
So in this case, in the device, you have a limited number of workers, right? It's not like it's a handful number of workers, right? So that's where we are able to use RSS, right? But if you have like hundreds of such workers, then RSS may not be efficient solution, right? But in your case, I think it's limited number of cores, 3 or 4 kind of thing, right?
Well, you can run as many workers as you want. I'm not going into too many details about the green device here, but it's a very special device, and it can run threads very, very efficiently. And you can decide, and you can tune it. You can decide how many different workers are you going to have. You can have a couple per core. You can have 5 cores doing something, and the other cores are running a different worker. And you can spread the traffic however you want. You have RSS, you have the hardware. You can decide that specific workers are doing one thing, the others one are doing another thing. Some worker is doing aging, the other worker is doing configurations. So this is something that you can control. It's not a 3 and 3 like in the picture.
Okay. And regarding the CT table, it's per device, or meaning, so what if both device has same 5 tuples? So how do you differentiate?
So both devices cannot have the same 5 tuple, because this is exactly the magic with RSS.
No, I understand that, but I'm saying if the CT table has such requirement where you are having an overlapping rules.
Wait, so if the CT table is configured for a specific connection, right, for a specific tuple, and yet it reaches the worker, this is what you mean?
Yeah, that's fine, yeah. Thanks, yeah.
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 Okay, so maybe a very simple question. So in essence, the interface that you're talking about is a binary interface of the data structures that are being shared. You'll ensure that they are essentially modified in the same way and look the same for all the possible architectures that you're having in your heterogeneous. Right? That plus the means of communication, be it the rings or another IPC, right?
Yes.
There is no sort of function level interface between those devices, the device and the host that we're talking about, right?
Right.
Okay,
Right.
thanks.
Yeah. Any other questions?
Do we have any other questions for Alex at all? If not, let's give him a big round of applause. It was a great presentation. Thank you so much.
Thank you very much.
That was great.